All right, Unit 5, Lesson 1, Antiderivatives from Derivatives, meaning if you can do derivatives, you should be well set up for this. So our goals today, you should be able to find basic antiderivatives. I'm based on derivatives you already know. Thing 2, like many times, if you can't do something, let's try to avoid it, rearrange into something we can do. And the thing we're going to do today is use division to rearrange integrals into easier forms to deal with. Here we go. So when we're doing antiderivatives as compared to definite integrals, we need that plus a constant. I don't know. Somehow we always forget because you're just like focusing on, hey, what's the antiderivative of this thing? And you forget to write plus c. Okay. Here we go. So this should be pretty easy. We're just going to evaluate the indefinite integral of secant squared x dx, which means we're trying to find the antiderivative of secant squared x with respect to x. Or another way to say that is, what function has the derivative secant squared? Tangent of x. And like I said, don't forget plus c. Okay, let's try that again. What has the derivative sine of x? We're trying to find the indefinite integral of sine of x dx. And, well, cosine? The derivative of cosine is negative sine. So negative cosine of x plus that constant. Like I said, pretty straightforward if you know your derivatives. This one, not quite so. You know, when you look at 1 over x, a lot of people think, well, maybe, let's change this color. Maybe I should change this to the indefinite integral of x to the negative first power dx. But then you'd add 1 to the exponent, you'd get x to the 0, which is 1, and there's no way that's correct. So it turns out you just think for a second, what has the derivative 1 over x? And the answer is natural log of x, but we need an absolute value of x in there. Uh-oh, I pressed something. Uh-oh, what the heck was that? Try that again. Okay, technical difficulties over. Turns out the microphone was on the spacebar. Okay, anyways, that absolute value seems to come out of nowhere. And why do we need it? In short, because of the domain. So the domain of 1 over x is x does not belong to, or 0 is not part of that domain, everything but 0. And domain of natural log is 0 to infinity. Or said another way, natural log only takes positive inputs. Man, I do not like that red. Okay, so here's the graph of 1 over x, which again clearly has a domain of all real numbers except for 0, and furthermore is differentiable everywhere except for 0. So if we graph that against, I have that next. Okay, so we'll do the graph in a second. On the right-hand side, I know we were doing antiderivative, not definite integral, but I just figured this would be an easier way to show it. So if we were going to do the antiderivative of 1 over x and the inputs were 2 and 4, that's no problem because 2 and 4 are positive. Okay, so that gives us natural log of 4 minus natural log of 2. Just trust for a second and then we'll put it on the graph. So we have to put natural log of the absolute value of x if these are negative, the bounds of integration, because, and you can try it in your calculator, try natural log of negative 2, your calculator is going to say error or, depending on it, just won't do that. And so just like numerically, we do our antiderivative substitute, and then, natural log of the absolute value of negative 2 is natural log of 2. Natural log of the absolute value of negative 4 is natural log of 4. And what I kind of want to point out here is we get the exact same value, but with the opposite sign. So at least that's something useful. So I wanted to have this first, but I don't really want to re-record this. 1 over x, you can see, has a domain. Again, we already saw that. And the domain of natural log of x is only positive inputs because the output of e to the x is only positive outputs. natural log and e to the x are inverses. So here is the graph of natural log of the absolute value of x. And, you know, there's some symmetry there. And so what did we just do? We found the area. White, in this case, is the worst color to use on a white background. Okay, so we found the definite integral from 2 to 4 of 1 over x dx, and that was this area here. Okay. Separately, we found the definite integral from -4 to -2 of 1 over x dx, which visually, you know, is doable. There's definitely some area there. And if we were paying attention back in fundamental theorem stuff, when we do area under a curve and that curve is below the x-axis, that's going to be a negative area. And so these two areas are the exact same size and shape, one positive, one negative. Hopefully that's a little convincing that we need the absolute value of x in there. You know, without, I guess that's saying this area doesn't exist because 1 over x doesn't have an antiderivative for negative inputs, which is poppycock. Okay. All right, back to some, this should still say easy stuff at the top. This one's pretty easy. Antiderivative of e to the x with respect to x, well, that's pretty easy. E to the x has the derivative e to the x. Don't forget your plus c. Okay, this one might take you a little bit longer, but again, you should recognize what has the derivative 2 to the x natural log of 2? Well, remember, e to the x has the derivative e to the x, and 2 to the x has the derivative 2 to the x natural log of 2. So that should be easy, unless you're realizing we forgot plus c. Don't forget that plus c. Okay, so if we can do the antiderivative of 2 to the x natural log of 2, we can do the antiderivative of just 2 to the x. And, well, we know it involves 2 to the x, but the derivative of 2 to the x is natural log of 2. So antiderivative here is 2 to the x divided by natural log of 2. Don't forget that natural log of 2 in the denominator, that's a constant. So we can ignore that, push it off to the side. That's the same as multiplying by, 1/3 or something like that. We can just ignore that as we do derivatives or antiderivatives. Okay, last couple of examples. You should look at x cubed minus 3x squared plus 4 over x and think, well, that's a quotient. So what you definitely can't do is the antiderivative of the numerator divided by the antiderivative of the denominator. The way I like to explain it is, derivatives and integrals are inverses, and there's a lot of shared things. So anything you can do with the derivative, like you could, we were just saying, when you're doing a derivative, you can just kind of bring down a constant multiplier, kind of ignore it, throw it in when you want. Likewise with antiderivatives. If I know we're not doing the derivative, but if we were doing the derivative of this quotient, we couldn't just do 3x squared minus 6x plus 0 over 1. We can't do the derivative over the derivative. We can't do that with an antiderivative, right? We have to do something different with a quotient. And the easiest thing to do is just divide. X cubed divided by x is x squared. 3x squared divided by x is 3x. 4 divided by x is 4 over x. So notice that's much easier. We took something complicated and turned it into something much, much easier. And so like I was saying, anything you can do with derivatives, you can do with antiderivatives, meaning we can do the derivative of terms added together individually. We can do that for antiderivatives. Antiderivative of x squared is x cubed over 3. Antiderivative of negative 3x is negative 3x squared. And the antiderivative of 4 over x is 4. Natural log of the absolute value of x, we just showed you that, plus that constant. Okay, now when you look at this, that's a little bit harder because, well, it's not terribly obvious what to do, but you should know x cubed minus 3x squared plus 4 divided by x plus 2. I'm going to have to rearrange so I don't have that quotient. And the answer is, well, we just have to divide. And I wrote that out ahead of time, assuming you just need a little bit of guidance. So we're doing long division. I suppose you could use synthetic division, who cares? And I did that off to the side with, just organized, so it's obvious what we're doing. And I'm going to replace, this whole quotient with x squared minus 5x plus 10. And then do you remember what you do with that remainder x plus 2? Oh, sorry. With this remainder, negative 16. We do negative 16 over that dividend, right? Divisor? Dividend? My sixth grade math teacher didn't help me out with that vocabulary. Okay. Anyway, so now at least 3 of the terms are much, much easier, right? The antiderivative of x squared, that's easy. X cubed over 3. Maybe I'll do that as we go. The antiderivative of negative 5x is negative 5x squared over 2. Antiderivative of 10 with respect to x is 10x. And then let's ignore the 16. I'll just bring it down. So now we're just thinking, what has the derivative 1 over x plus 2? And the answer is natural log of the absolute value of x plus 2. Right? Because if you think about that, what's the derivative of natural log? 1 over the input, chain rule times 1. No, that works out. Did you realize we forgot something so far? Plus a constant. Okay. All right, one last one. And again, we're going to divide. You see a quotient, you're like, hey, what do I do? And the answer is eventually you might have to do u substitution. But we're not there yet. So x cubed minus 3x squared plus 4 over x cubed, we can just divide. X cubed divided by x cubed is 1. 3x squared over x cubed is 3 over x. And 4 over x cubed is, 4 over x cubed. Pretty easy. Now 3 over x, hopefully we're realizing that's going to have an antiderivative of 3 natural log of the absolute value of x. But 4 over x cubed, let's rewrite that so we can use the power rule a little bit easier, because, I don't know, people get confused there. So antiderivative of 1 with respect to x is x. Antiderivative of 3 over x is 3. Natural log of the absolute value of x. Those inputs might be negative. And let's see. What do we do to the exponent to do a derivative? You subtract 1. So to do the antiderivative, we'd add 1, and literally add 1. So negative 3 plus 1 is negative 2. And then we have to think, if we were doing the derivative, that exponent negative 2 times whatever coefficient we're about to write is going to give us positive 4. And so that's going to be a negative 2. Right? So you could think negative 2 times negative 2 is 4, x to the power negative 3 when you'd be doing the derivative. Okay. Oh, dang it. Did you forget? I didn't. Plus c at the end.